Good day and welcome back for the second part of our discussion on the fundamental theorem of calculus. In our previous discussion, we introduced what we refer to as part one of the fundamental theorem of calculus. And it allows us to quickly and conveniently differentiate this function of x, which we previously referred to as an area function. And remember, when you have this precise form, you're integrating from some constant, and it could be any constant you choose, to a upper limit of integration, which is the variable x. This becomes the simplest possible derivative we can evaluate. We substitute that quantity x in for f of t, and we get back f of x. And we finished our previous discussion by working through several common examples. But after a few examples, a natural question does arise. What if instead of having an x as our upper limit of integration, we have a function u of x? Then how could we go about handling this? And it turns out we really just have a chain rule problem in disguise. That is to say, we're taking this new function u of x and we're putting it inside or composing it with this old function. So to maybe make this a bit more clear, let me add a few details to the side. If we let g of x be defined as the function from a to x of f of t dt, and note that this is a function of the independent variable x, so whatever quantity gets substituted in for x, it then becomes our upper limit of integration. So for example, if we had g of the quantity u of x, the u of x is what becomes our new upper limit of integration. So this would be a to u of x, f of t dt. Likewise, we know from above in our previous work precisely what the derivative of g is. G prime of x, as we calculated above, is simply f of x. So back to the problem at hand. This is really differentiating the composition g of u of x. And when we differentiate a composition, we use a chain rule. The chain rule tells us the derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside function. G prime is equal to f of x. So g prime of u of x is f of u of x times u prime. And for convenience, let's summarize this in a slightly more compact formula. The derivative of the integral from a to u of x of f of t dt is equal to f of u of x times u prime of x. And the big observation I want to make is that our intuition is precisely the same as it was before. As long as we're integrating from a constant a up to now some function u of x, you take that function u of x and you substitute it in for t. That gives us the f of u of x. And by the chain rule, we multiply it by the derivative u prime of x. So a more general version of this previous formula where we substituted in x and we multiplied by its derivative, which is just 1. Let's go ahead and apply this formula to a few examples, similar to the type of problems we ended our previous video with, except now instead of having an x, we have a function of x. If I want to differentiate this, we're going to use this boxed red formula above. We have the desired form. We're going from a constant to a function of x. So we simply take that function of x, we substitute it in for each t. That will give us the f of u of x. Then we multiply by u prime of x. So writing these details out, we substitute in that cosine, so cosine x plus sine of cosine x, multiplied by the derivative of cosine x. And you, of course, could do that in one single step, but now we have cosine plus sine of cosine multiplied by minus sine x. And if you want to compare it above to our red boxed formula, we have f of u of x times u prime of x. For the final example that we will cover, note this doesn't precisely have that desired form we would like to see. We are not integrating from a constant to a function of x. We're integrating from a function to a function. So in order for us to apply our new formula, we first need to manipulate this using properties of the definite integral. And let me just give you a reminder. One of the key properties we saw for the definite integral, and now it's been a few sections back, is that if you want to integrate from a to b, and c is any other value, you could integrate from a to c, and then add on to this the integral from c to b. So we will do precisely that in a way that will allow us to introduce this constant. So I'm going to go ahead and pick my c value in this formula to simply be a constant above. So we will rewrite h of x as the integral from 5x to your favorite constant. Here I'm going to choose 0 just for convenience. Cosine of w squared plus the integral from 0 to sine x of cosine w squared. And note, once again, there's nothing special about using 0. You could choose whatever number you prefer in this case. And at this point, it's a great opportunity for you all to get in a little bit of practice. So let's pause the video. I'd like you to use the formula above, the template that we have from our previous example, to see if you can now find the derivative of this function h of x. So hopefully you've paused the video and thought about this for a moment. And the observation is that the second term is precisely in the form we want. We're integrating from a constant to a function of x. We're good to go. The first term is not in the desired form. We need to switch around the order of integration. And if we want to switch around the order of integration to make it more convenient for us to differentiate it, we need to introduce a negative sign, another one of our properties of the definite integral. But once we have done so, we are now ready to differentiate. So just working term by term, and I will do this all in a single step. We take our 5x, we substitute it in for this variable we're integrating with respect to, w. So this would be the cosine of the quantity 5x squared times the derivative of 5x. Plus, we do the same thing again now with the second term when we differentiate. That function sine x gets substituted in for w. So cosine of sine of x quantity squared times the derivative of sine, the cosine. And I do want to caution you, the most common mistakes I see in these types of problems is forgetting to multiply by the derivative, which is required by the chain rule in our new formula. So definitely worth taking some time practicing a few examples to making sure that you understand this idea. In our next video, we are finally going to be ready for the second part of the fundamental theorem of calculus, which will provide a convenient and hopefully efficient formula for evaluating definite integrals. So stay tuned and take care.